Hey y'all, it's Mr. Boyden back at it again, and today we're going to start our final video of the segment. We're going to be talking about the vector equation of a line. One of the things that I wondered when I first learned about vector equation of a line is why would I ever care to write a line in terms of vectors? Because in my mind, I already knew how to do things like y equals mx plus b, and I was really good at that, and I thought, wow, it'd be better if I could just keep doing that. So I want to start this video by talking about not like what the mechanics of the vector equation of a line are, but why in the world there would be reasons to actually write it out. Because what we're going to see is we're very comfortable with y equals mx plus b, but the vector equation of a line is going to look a little bit more convoluted than that, so there must be some good purpose for that. And here's what I believe it is. Okay, in Algebra 1, you would do questions where you'd be given a graph, and you'd be asked to find where two lines intersect. And you'd find their intersection, maybe you do it algebraically, graphically, in a table, and then you say, yay, I'm so smart, I'm so good. But some contexts really start to fall apart when you do that. Like, let's say that you have two people who are walking, and one person's walking across a field like this, and one person's walking, they're starting down here, and they're walking across a field like that. I guess we'll give that a y-intercept. And then the question asks, do these people walk into each other, or is one of the people going to be forced to slow down or change their path so they don't actually cross each other? And it turns out that if you're just using this format of an equation, y equals mx plus b, there actually is not a way to say if those people are going to bump into each other. Because, for example, let's say this person started walking at 9 a.m. and this person started walking at 9 p.m. This equation does not have a way to represent that information. All we know is that at some point the two paths they were walking on crossed. Heck, we don't even know if they saw each other. Same thing would be true like if two boats were going to crash, or if two airplanes are going to crash, or two cars are going to crash in an intersection. There's no way of knowing if that's going to be a problem based on what we learned in algebra. So that's why we need something like this, so we can actually find out if two objects were in the same place and at the same time. Because in order for there to be a crash of two people or of two cars or whatever, they would both have to be trying to occupy that same location at the exact same time. And if it's different times, they're all good. So with that sort of lengthy explanation, let's get into sort of the mechanics and the way we write this stuff. The base concept is this. If you wanted to go on a trail and go for a hike or something like that, you'd have to do two things. First thing you have to do, and you do have to do them in order, by the way. Number one is you have to get to the trail. Like when you wake up in the morning, unless you're sleeping on a trail, which, I mean, maybe you are, I don't know. But unless you're sleeping on a trail, when you wake up, if you want to go for a hike, you first have to get to some sort of a trail. So we have to get to the trail. Once we're there, if we walk in the correct direction on the trail, we will continue to be on the trail. If we walk in a different direction, we will not continue to be on the trail. And I hope that's really intuitive. That's like the basic makeup of how this works though today. So let's make up an example so you can see what I'm talking about. I'm just going to make up an example like back from Algebra 1. So let's do like y equals 3/2 x minus 4. So let's graph that. We start by going down 4, 1, 2, 3, 4. And then from there we go up 3, 1, 2, 3 over 2. And up 1, 2, 3 over 2. And so I got my dots. I'm going to make my sketch. There's my line. And we remember that lines go both directions. Now let's play around with how we can write the equation of a line. So what IB is going to have in their formula book is R equals A plus TB. And I want you to notice right away the similarities between this and what we learned back in Algebra 1. So they have some sort of loner number. Up here we called it the y-intercept. Down here it's called a position vector. And I'd like you to remember that a position vector is always coordinates. Up here we have mx, that was the m was the slope. B is not the slope, t is a variable, but b is what's called a direction vector. It tells us what direction the line is going. Okay. So there's a lot of similarities. So what we're going to do, if we know the position vector is the coordinates, all we have to do to get to the trail, we have to find some location, or you think of it like a trailhead maybe, we have to find some location where we can access the trail. So what I'm going to do to write this equation of the line, I'm going to pick coordinates of a point. I think I'm going to start with this one. And it doesn't matter which one you pick. I have 3 that are obvious here on the screen. You just pick one of them. Okay, so 2, 1. So that's the first point. Plus t times a direction vector. You can think of a direction vector literally as directions, like how do I get from one point to the next? Well, to get from one point to the next, one way to do that is to go right 2 and up 3. Now, when I taught this yesterday, some students said it should be 3, 2. Be careful. Remember, that first number is the x component. It's telling you how far to go left and right. The second number on the bottom is telling you how far to go up and down. And it's definitely 3 up, right, 2, so that's what we want. This is one way of writing the vector equation of this line. There are others, however, and I want to demonstrate that to you. Another way we could have started this is 0, negative 3 right here. Or, excuse me, 0, negative 4. Because it was down 4, that was our y-intercept. So 0, negative 4 would have been another way to start this. That's that point. Because again, it's coordinates of a point. It doesn't matter which point. And I want you to be aware, another way we could have done this over here is we could have done negative 2, negative 3. Because what would that mean? That would mean to get from any one point to the next, you'd go left 2 and down 3, left 2 and down 3. And yeah, that just sends us down in this direction. So that still has you on the line, still has you on the trail. Because when you get to a trailhead, sometimes there's more than one way to go. They're both on the trail. Okay, and that works here too. So sometimes people get frustrated because when we learned about slope-intercept form, that form is unique, meaning there's only one right way to write the equation of the line in that form. But with vectors, there are multiple ways, as we've illustrated 2 of them here. There are multiple ways to write the correct version of the line. So be aware of that. If yours doesn't match perfectly, it doesn't mean you're wrong. It means that we need to think carefully about whether or not it's wrong. Okay, because you may have something totally different and it may still be perfectly right. So let's do an example. A line goes through 2 points, P and Q. We're given the coordinates of those points. We're asked to write the equation of the line and then determine if the point, negative 291, is on that line. Okay, so let's do it. What we're going to remember is that first we're going to write the position vector. And the position vector is coordinates. So we need to pick coordinates of a point on the line. Now, this example is nice enough to give us 2 sets of coordinates. It does not matter which one you pick. P came first, that's the one I'm going to use for this video, but you could use Q, it doesn't matter at all. Okay, so 1, 3, 2. That's how we get to the trail, so to speak. Plus T times the direction vector. Now, yesterday when I taught this, a lot of people thought this negative 291 was the direction vector. But that's not really what that says. We are asked to determine if the point is on the line. It's not telling you how to get from point to point. So the question is, if we're at 1, 3, 2, how do we get to another point on the line? Well, let's see. What is another point on the line? Right here. So how would I get from P to Q? That's as simple as saying, how would I get from 1 to 0? I would have to go left 1 to get from 1 to 0. So negative 1. And then I'd have to get from 3 to negative 1. And that's the y component. I would have to go down 4 to get there. And then I'd have to get from 2 to 4. I would have to go out 2 to get there. So there's the equation of the line. Now, we're asked to determine if the point negative 291 is on the line. So what I'm going to do, I'm going to try to figure out if this line is ever equal to those values. So I drop them in. I say, I don't know. I'm not sure, but if it's possible, then there'll be some value of t, because that's the only variable, there'll be some value of t that makes that equation true. So what we're going to do is we're going to solve this and see if it's true. Now, what I'd like you to think of this as, not as one equation, because that's going to be overwhelming. I want you to think of it as 3. I'm going to write out the first one. How about this? 1 minus t equals negative 2. How did I do that? 1 plus negative t, that's 1 minus t, equals negative 2. There it is. Let's write another one. 3 minus 4t equals 9. 3 plus negative 4t, that's why it's minus 4t, equals 9. And the bottom one, 2 plus 2t equals 1. Now we're going to solve these. Let's see. So if I add t here and I add 2, I get t equals 3. And you can show the steps if you want. I'm going pretty quick, but show the steps if you like. Here I get 2t equals negative 1, so t equals negative 1/2. And over here, I'm going to move the 4t to the right, and I'm going to subtract the 9t, so I get negative 6 equals 4t, so I get t equals negative 3/2. So I got 3 different values of t. The problem is, what I need is for one value of t to pump out that point. Let me show you why really quickly, because that might not be intuitive yet. Let's say that t was negative 1. And this is just a demonstration. I'm not answering the question, but I'm showing you why this means that the answer is no. No, it is not on the line. Okay, here's why. Because any single value of t will pump out a point. That's what it's saying. It's saying you start here and you start here, you do this, and you get onto the line, but this has different values of t. So like, for example, if t was -1, the equation would say 1, 3, 2, and then if I distribute a -1, if that's -1, distribute that in, I get plus 1 for -2. And what we get when we do that, we get 2, 7, 0. So what that's an indication of is that the point 2, 7, 0 is a point on the line, because one value of t produced those values. So that is a point that's on the line. It's like if we were asked, find a point that is on the line. Well, we've done that now. Okay, but that's an indication that no, this point's not on the line because there's not a single value of t that produces it. Let's do another example. And this one I've tried to write in the most confusing way possible. And I know that seems kind of cruel, but what would be really cruel is if you had to see the most confusing example on a test and you never got to see it in class or in a video. That would be really unfair. So that's why we're going to do this one. Take a minute and write it down. I think what will be most helpful here is if we get rid of the linear combination form, because there's so many letters in this right now, so many parentheses and symbols that they're not unnecessary, they are necessary, but they might feel overwhelming. Okay, so what we might do first is rewrite these equations in a different form. So I'm going to do it like this. So L equals, remember, this I right here is just telling you it's the x component of the vector. So the x component in column form goes first. So that's 2 minus 3s. And let's get the next one. J just reminds us that that's the y component. So it says 1 plus s is the y component. So 1 plus s. And we have 4sk, so I guess that would be 4s. And let's also do the m vector. So we get -1 plus 3t, and we get 3 and 7 minus t for that one. Now, look, guys, if that went really fast for you, then pause the video and think about it for a second. If you look at where I got these from, you definitely will be able to put the pieces together. I know sometimes when we're watching a video, we're like, oh, it's 20 minutes, I want to do it in 20 minutes. This example might take you longer to understand than the video length. So like if this is a 5-minute example in the video, you might have to watch it 2 or 3 times to really understand it. That's okay, that's normal. Okay, this is a pretty confusing example for a lot of people, so you would be known as normal if you're struggling with that right now. Okay, so we've written these out in 2 new forms, and we're asked to find what point do the lines have in common. Okay, that's the exact same thing as asking what's the intersection of these lines. Now the way it's written, it's not asking if they intersect. It's saying they do, and it's asking where they intersect at. So now we're going to try to figure that out. If I wanted to find the intersection of 2 lines, if they were in common, that would be the place where they are equal. So all I'm going to do is set these 2 equal to each other. And a lot of people look at this and go, oh, it looks like too much, I can't do this. And guys, I mean like high-level IB students sometimes, like, oh, it's scary, it's horrible. It's not. There's 3 equations. Here's one up here on the first line, and one here on the second line, one on the third line. So I'd like you to look at it and see which of those 3 equations looks easiest, because I want to do this with a minimum amount of work. So what looks easiest? To my eyes, this middle equation looks pretty easy. 1 plus s equals 3. Yeah, I think s equals 2, so let's go with that. Okay, now if s equals 2, that means I can plug that 2 in right here, because we now know the value of s that produces an intersection. So let's plug that in. So that would be 2 minus 3 times, oops, I wrote s instead of 2. 3 times 2, and 1 plus 2, and 4 times 2. And so I can simplify that out. So that would be 2 minus 6. So that'd be -4, 3, and 8. So here's what it means. It means that the equation on the left is telling us that that's the intersection of the 2 points. We're going to double check and make sure that's true. So we got to make sure the right line agrees that it actually has that point. So what we're going to try to show right now is that the line M does achieve that point. So let's do that. It goes like this. What we're going to do is we're just going to set them equal. Now this is going to look very similar to what we did in the last example, because, well, it is very similar to what we did. Okay, so 3t and 3, and I'm just writing this stuff, just bringing it on down, and 7 minus t. And what we're going to do is see if there's a single value that makes this true. So notice, because we worked on the middle line already, 3 equals 3, that's obvious, there's nothing more to do with it. Let's deal with this one on the bottom. 8 equals 7 minus t. You can do algebra steps if you want, or you can just look at it. I hope you can see that that means that t is -1. Like 7 minus -1 is 8. Some people here go, wait a minute, if s is 2 and t is -1, those don't match. That's okay. They're different variables. They don't have to match. So what we have right now, we know that t is -1. We need to get the same value of t out of this equation. So let's see if we do. So -4 equals -1 plus 3t. I can add 1 to both sides, so I get -3 equals 3t. Divide by 3, and -1 equals t. So we have verified now that a single value of t produces these coordinates, and a single value of s produces those same coordinates. Therefore, what point do the lines have in common? I'm going to write my answers over here. The point they have in common is, well, these coordinates, -4, 3, 8. And that's the work that's necessary to answer the question. Let's go to part B. We're asked for the angle that's formed at the intersection. Here's what gets a little bit confusing about a question like this one. I want to write these questions out in the original form we had, so here's what I mean. I'm going to do 2, 1, 0 plus s times -3, 1. I guess I'm pointing so you can see where I'm getting these from. 3, 1, and 4. So notice those are all the numbers that were next to an s. And then we're going to write the other one as -1, 3, 7. So notice I'm just plucking off the numbers that didn't have a t next to them. And the numbers that did have a t were 3 and -1. And so there's a t. And then if they don't tell us what's in the middle, it's 0. Okay, so there's no t there, so that's going to be a 0. So what I'm looking at right now is I'm asked for the angle. I'm going to label really quick. These first set of vectors are the position vectors. The second set of directions are the direction vectors. And so the question that I have for you then is, if we're asked to find an angle between vectors, what do you think matters more? Do you think the direction of the vectors matters, or do you think the position of the vectors matters? It turns out that if you have a constant direction but you move the position, the angle doesn't change. But if you change the direction of two vectors, like if you have two vectors like this and this one gets changed so now it's like that, the angle does change. So what I would like you to know, when we're asked what angle is formed, they're specifically asking us about the direction vectors. And previously, we learned how to find the angle between two vectors with cosine. So we can jump right to cosine inverse. And we're going to do dot products divided by product of magnitude. But what you need to understand is that we're not using this whole form of the vector. We're not using the position vectors. We're only going to use the direction vectors because that's the only thing that impacts an angle. So let's do it. Let's do a dot product. -3 times 3 is -9. And 1 times 0 is 0. I'm not even going to write it. And 4 times 1 is, times -1 is -4. And let's do the magnitudes. So square 'em, add 'em, root 'em here. That's root 26. And square 'em, add 'em, root 'em here. That's root 10. So excuse me for a moment while I go type this in a calculator. And we'll see what I get. All right, so for the numerator, I'm going to type in -13 just to make it quicker. Go down into the denominator, square root of 26 and square root of 10. And I get 144 when I round it to three significant figures, 144 degrees. So here's what I'd like to impress upon you. This calculation was not hard. That's the deal with vectors, guys. The calculations are never hard. There's no single algebraic thing we do that's really going to challenge you very much. The challenge is all in the concept, because here you have to recognize that in order to find an angle, you're only looking at the direction vectors. Okay, people make that mistake, and that's why they get this type of question wrong. They'll do things like take the two position vectors, or add the position and the direction vectors. Can't do that. They're not like terms. There's variables there. Or they'll just take this vector and that vector, but then they're only using one line. So make a note for yourself that this is a common mistake a lot of people make, so you don't have to make that mistake. I'm trying to call it out for you. So direction is what we're going to use when we want to find an angle. Guys, that's all for today's video. I think you're ready for some practice, so I hope you enjoyed it. Hope it's helpful, and we'll see you next time.